Well, let me continue with pile capacity. In my previous lecture, I just stopped how to find out frictional how to calculate the capacity of a single pile, and there as I have shown that the pile at a general pile general type of pile I have shown, that means there will be frictional resistance and base resistance, and I have shown some terminologies, that means F is unit skin friction, AS is the surface area of the pile and all those things. And now, we will go in detail finally to arrive at the capacity actually in terms of pile capacity, in terms of pile dimension, that means diameter and length, and then soil properties, and then soil to pile, that surface condition based on some frictional coefficient to be used. So, in terms of that finally, you have to arrive at the capacity of the pile. So, we will just continue with that. Let me so I have shown actually earlier that pile actually axial pile, but it is for compression, and we have seen that there was a tip resistance and there was a frictional resistance and tip resistance. But pile can be also used as uplift actually tension. In that case, you can see here, if there is T ultimate applied here, there is no chance of having tip resistance, only frictional resistance. Pile will be held by friction only. If I pull like this, the pile, entire pile will be held by the frictional resistance developed between the soil and the pile. So, because of that, you can see on the around the surface of the pile we have the friction, and then finally, what should be the allowable tension can be applied. So, Q s frictional resistance you have to calculate divided by factor of safety plus W. W is the load in the pile of the weight of the pile. So, these are the things. So, we will not discuss much, because pile most of the time 99% actually used for compressive load, axial compressive load. So, we will try to concentrate on how to estimate the pile capacity for compressive load. So, let me go to the next slide. You can see as I have told before, that Q ultimate will be equal to Q friction per Q tip, and the load is transmitted to the soil surrounding the pile by the friction or adhesion. That means, if there is a pile, so surrounding the pile, I am just showing the elevation actually. So, it will be like this. So, by friction or adhesion between the soil and pile, there will be frictional resistance load. So, that some load will be transferred here actually, and side of the pile, and or the load is transmitted directly to the soil just below the pile tip. So, that means, there actually directly below this load also will be transmitted. So, if I apply load here, so some load will be transmitted here by friction and adhesion, and some will be directly transmitted here, and these two together, this is called Q tip, and this is called Q friction, Q f. Q f or Q s, Q sometimes Q f means Q friction, and sometimes Q s also used, that means Q skin friction. So, skin actually the initial of skin is used sometimes, Q f or Q s, both are same, and here actually Q tip or sometimes Q end also they people are using, Q b also sometimes use Q base, all those things are a similar thing. So, that means, in general Q ultimate will be Q friction plus Q tip, and Q friction will be F multiplied by A surface. So, F is the unit skin friction, somewhere here actually unit skin friction, that means, what is the value, and then you have to multiply by the surface area. If it is a cylindrical pile, then what will be the A surface? A surface will be equal to, for a cylindrical surface, pi multiplied by d multiplied by L. What is that? That means, the here actually if I see, this is the pile top view, that means, perimeter is pi d, and the surface vertically up to ground surface if you go, that if you multiply, then you will get entire vertical surface that means around the pile the entire area is resisted. So, that is why the surface means entire cylindrical surface of the pile to be considered. So, A surface actually pi d into L, and Q tip here, Q tip actually Q multiplied by A t. A tip is actually area of the base of the pile, and Q is actually is nothing but bearing capacity of the soil at this depth. So, that to be estimated. So, this is in general terminology while calculating bearing capacity or capacity of the pile, you have to do this. So, let me go to the next slide, and you can see I have again elaborately defined all those terms. Q ultimate means ultimate capacity of the pile, Q friction means pile capacity furnished by friction or adhesion between the soil and pile and the sides of the pile. So, Q friction, so Q f or sometimes Q s is nothing but pile capacity furnished by friction or adhesion between the soil and the sides of the pile, and F is the unit skin friction or adhesion between the soil and the sides of the pile. And so, what should be the unit? So, ultimately that unit skin friction multiplied by area, we are getting the load. So, that means it will be area should be kilonewton per meter square actually in the pressure unit. A surface actually vertical surface area of the pile. So, that will be actually for a cylindrical with d diameter length L, A surface equal to pi d into L, and A tip is the area of the pile's tip, that means bottom of the pile what is the area, and if it is a uniform cross section throughout the length of the pile, then pile tip will be equal to the pi diameter of the pile itself. So, A tip will be nothing but pi d square by 4 cross sectional area of the pile, and Q is the ultimate bearing capacity of the soil at the pile's tip. So, we have learned actually bearing capacity of the soil for shallow foundation, and you know the pile is a deep foundation where shallow foundation actually used to be at within 1 or 2 meter, whereas a deep foundation or pile foundation will be beyond 10 meter depth actually most of the time. So, it will be 10, 15, 20, 30, 40 anything it can be. So, at a great depth bearing capacity calculation will not be same as we have done in the shallow foundation bearing capacity. So, what will be the bearing capacity at the ultimate bearing capacity of the pile tip, that has to be also learned. So, we will discuss that also. And you can see here we have discussed in general that pile will have resistance from the surface, surround the surface and at the base, but and also we have classified different type of end bearing pile, friction pile and a general type of pile. And you can see here it is the end bearing pile Q tip will be predominant. So, though sometime we say end bearing pile, that means pile will be resting on a very steep strata or on rock. So, in that case it will have actual capacity will be coming from the pile tip only, but sometimes some amount of resistance will be there from the side also. So, in general we can say when it is the end bearing pile, we can say Q tip will be the predominant, that means larger quantity of resistance will come from the base of the pile, whereas is the friction pile, where it is a friction pile, the friction is predominant. The friction pile, though it is a friction pile and throughout the depth actually frictional resistance is there, but ultimately pile resting on the some soil. So, that whatever may be the soil, because of the bearing capacity of the soil, some resistance also will be at the tip, but that contribution from the tip for friction pile will be sometime negligible or small compared to the frictional resistance. So, because of that we can say for frictional pile that Q friction is the predominant. So, you have Q friction and Q tip, there are two component for each pile. When the end bearing pile, this is predominant, when the friction pile, this will be predominant. That is the one thing I wanted to mention here. So, sometimes we ignore. So, when it is a end bearing pile, Q friction we ignore, and when it is a friction pile, sometimes Q tip we ignore. So, that is the point I wanted to highlight here. Now, pile driven inside. So, again as I have mentioned that I had to find out the capacity of the pile, then pile when it is driven in sand and pile driven in clay, capacity will be different and calculation everything will be different. So, because of that one by one I will take, first of all I will take pile driven in sand, how to find out the capacity and what should be the capacity, finally outcome will be there. So, let me see here actually total capacity again is the frictional capacity and friction capacity and end bearing capacity. So, Q ultimate will be Q friction plus Q tip, these two things we have to estimate. And next one, you can see that Q friction will be F multiplied by the A surface, already I have mentioned F multiplied by A surface. A surface already, if it is a cylindrical pile, then we know the what is the A surface, but F to be estimated. F can be evaluated by multiplying the coefficient of friction between the sand and pile surface, that is called tan delta, by the total horizontal soil pressure acting on the pile. So, that means, if there is a pile is driven something like this, and as usual because of the soil pile there will be vertical pressure. So, different depth there will be different vertical pressure. What is the vertical pressure here? That will be gamma times h actually, suppose if the height is h. So, vertical pressure is gamma times h, and then coefficient of lateral earth pressure if you multiply, then there will be horizontal, the vertical pressure from initially we will get vertical pressure, from there multiplying by the lateral earth pressure coefficient, then you will get the horizontal pressure, and after getting horizontal pressure you multiply by tan delta. Okay. If that your lateral pressure is P suppose 20, then multiplied by tan delta suppose 0.2, then your unit skin friction will be 0.4 or not 0.4, it will be 4. So, unit skin friction will be 4, and then capacity will be equal to 4 multiplied by pi this pi d multiplied by L. So, this will be the capacity, frictional capacity. So, that means, if, here to calculate the frictional resistance, A surface is known already, you have to find out F. How to find out the F? First find out the vertical pressure, so along the length at different depth you find out the vertical pressure, then by multiplying by the lateral earth pressure coefficient you find out lateral pressure, then multiplied by the frictional coefficient, that is tan delta, that will be your unit skin friction. Now, if the unit skin friction is constant throughout the depth, then we can find out the capacity like this, but your unit skin friction will not constant, mainly because if I change from here to here now, then sigma v will be less here, then lateral earth pressure will be constant. So, the horizontal pressure will be less here, and if you multiply by another constant, then ultimately your unit skin friction will be lesser than at this depth. So, that means, and at this depth at the surface your vertical pressure is 0, the lateral pressure also will be 0, multiply by coefficient of friction, then it will become 0. So, that means unit skin friction will be 0 here and it will be maximum here. So, it may vary by some means, generally it can vary linearly, that we can show you later on. So, that means unit skin friction will be varying by some way, and then if it varied, then we will not be able to estimate the capacity like this. If it is a constant, then pi d L, the surface area multiplied the unit constant frictional resistance, but if it is variable, then you have to do something else, that I will show you later on. And you can see, as I have mentioned, that between the material and the soil type your tan delta will vary. That means, what I have said, smooth pile and then cohesive soil, smooth pile and cohesionless soil. Similarly, rough pile with cohesive soil, rough pile with cohesionless soil. So, then there are so many combinations like that. So, you can see in general, if there is a material, generally most of the time based on material actually fix the tan delta, and it can be vary little bit in between. And so, you can see here material based on concrete, generally we take a value of tan delta equal to 0.45, if it is wood slightly less 0.4, if it is steel then it will be still less 0.2, and if it is steel with rough steel, then it is again same as concrete 0.4, and still corrugated, then it will be equal to tan phi of sand. Whatever phi value is there in the sand, then you find out tan phi will be equal to tan delta when corrugated steel pile is used. And horizontal soil pressure, this is the one very important, as I already have explained that way. And you can see that horizontal soil pressure, this is the pile. Once again I will do here, and at this point, suppose I want to do horizontal pressure, at this point vertical pressure is 0, then horizontal pressure also 0. At this step vertical pressure will be some value, horizontal pressure also bigger than 0. So, maybe suppose the value is somewhere here. So, I can, this will be definitely linearly varying, gamma times h, it is linear. So, it will go this to this, and if I now reach here, then definitely a value will be something like this. So, it will be like this. So, lateral pressure actually is continuously increasing, okay. But for calculation of unit skin friction, we will not consider this concept. You can see that total horizontal soil pressure acting on the pile is function of effective vertical pressure of soil adjacent to the soil. So, that means what is the vertical pressure, horizontal pressure, lateral pressure, it depends on effective vertical pressure, that already I have told you. First of all, you find out vertical pressure, then multiply by the lateral earth pressure, then you will get the horizontal pressure. Now, however, it has been determined that the effective vertical pressure of soil adjacent to a pile does not increase without limit as depth increases. So, this lateral pressure for the pile, in fact, maybe it may increase, but for calculation of capacity we will not allow, or we will not take that increasing up to the pile length. So, that is what it is without limit, actually do not increase. So, that is what it is mentioned. Instead, effective vertical pressure increase at a depth increases until a certain depth of penetration is reached, and below this depth, which is called the critical depth, that means that variation of horizontal pressure adjacent to the pile increasing linearly up to certain depth, and then we keep it constant. So, that means instead of this way, if I imagine that up to this the horizontal pressure is increasing linearly, and from here to here I will keep constant. So, then horizontal pressure diagram become like this, your horizontal pressure diagram become like this, okay. And depth up to which we are considering the variation of lateral pressure, that is called critical depth. So, that means instead of considering the horizontal pressure increasing up to the length of the pile, bottom of the pile, will restrict the variation of lateral pressure linearly up to a particular depth, that depth is called critical depth, and beyond critical depth we consider that lateral pressure is constant. And this critical depth, how it will be determined, there is a guideline, I will tell you in the next slide. You can see now the diagram again drawn here, but neatly you can see here, if I calculate sigma v dash at any point, suppose here sigma v dash, if I calculate here, what will be here? It will be, if it is no water table, it will be gamma times h, and if there is water table, so it is underwater table, it is gamma submerged times h, because it is effective vertical stress you have to calculate, actually effective vertical stress, okay. And then lateral pressure will actually will be multiplied by whatever k value. If you multiply, then it will be lateral. So, if you multiply, then you will get the horizontal pressure, and this vertical pressure actually instead of lateral pressure, actually we do not know, we know only vertical pressure. So, if I restrict the vertical pressure, then automatically I can restrict the horizontal pressure, because lateral earth pressure coefficient is constant. So, that is what it is shown, that whatever I have discussed in the previous slide, that variation of vertical pressure will be increased linearly up to some depth, that depth is called critical depth, and beyond depth it is called, it is taken as constant, that is sigma v dash. Up at this depth, whatever value you get, you keep it same everywhere, okay. And this DC is the critical depth, as I have mentioned, and approximately it can be estimated 10 times the diameter of the pile for loose soil and 20 times of diameter for dense soil. So, that means this DC how much depth, up to how much depth this linear variation will consider. When it is loose soil, we will consider only 10 times diameter of the pile, whereas if it is a dense soil, then we will use 20 times the diameter of the pile. Okay. So, that means, if there is a pile, like this, and you will see the soil condition, and based on that I will fix the critical depth, and then I will draw the vertical pressure diagram, and then using this diagram I can find out the capacity of the pile. You can see now, if the variation is like that, you can see if your variation something like this, that means at any depth, if I take a small length, then it will be at this depth actually vertical pressure actually gamma times z, and then if I multiply it by k, then it will be lateral pressure. Then if I multiply it by dz, then it become force, and then if I multiply by tan delta, then it will become unit skin friction, and now I have taken this z as a variable. Now, if I integrate this one from 0 to suppose dc, okay, then I will get the, because of the friction, the load taken by the pile is I can find out. So, that is what it is shown is here actually. You can see first one integrated 0 to dc, and see out of these so many variables, k is constant, tan delta also constant. So, k and tan delta I have taken out, and after getting the unit skin friction, what you have to do? You have to multiply it by pi times perimeter, because length also already variable, we are taking length is variable, length is coming by integration only how to, and I am suppose if this is the pile, I am considering at one point, then around the pile there will be n number of points. So, how to consider that? But just by multiply by pi d. So, that means this multiplied by this pi d will be actually your skin friction for this small element. But if I want to find out from 0 to dc, then you have to integrate. So, that is what it is shown, integral symbol is used 0 to dc, gamma z dz actually multiplied by k tan delta pi d. So, this is one part, whatever I up to this, and beyond this actually what happened, if the length of the pile is L and critical depth is dc. So, remaining depth from here to here actually this is L minus dc. So, length you have got L minus dc, and the lateral pressure is gamma times dc. This is actually vertical pressure is gamma times dc, and then multiplied by k, then it become horizontal pressure, then multiplied by tan delta and pi d, then I will get your so L minus dc already I have taken here. So, that means from here to here, if I want to find out what I could have done, I could have done gamma times dc multiplied by k multiplied by tan delta, that is constant, this part is constant throughout the depth. So, because of that you can multiply by actually length pi d into L, pi d multiplied by L is how much here? L actually L minus dc, sorry L minus dc. So, that is the thing is done here, L minus dc gamma times dc, L minus dc gamma times dc, and tan delta pi d is there outside, k pi tan delta pi is outside. So, there are two components, that means we are integrating from here to here one part, and then here actually unit skin friction throughout the depth is constant. So, that is what L minus dc gamma dc is k tan delta pi d, this is so. So, that way if I simplify now, or I can write differently, maybe two part, that will be convenient for you. Let me write once again, let it be clean. So, it will be gamma times z dz multiplied by k tan delta pi d, and this will be 0 to dc. So, that means when I am considering this is dc. So, this one give you this is pi, actually this is pi times d. So, this is giving you load from here to here, and remaining depth here actually unit skin friction will be constant. So, unit skin friction will be how much? This will be plus gamma times dc multiplied by k, that become unit skin friction, and multiplied by your tan delta, that become unit skin friction. And then if this is constant, then surface area you have to multiply. Surface area will be pi L minus dc, pi multiplied by d multiplied by L minus dc. So, you can see this part is written. So, this plus this is nothing but this, actually I have little differently I have written here, because these are the common thing, k tan delta pi d, you can see k tan delta pi d common, here also k tan delta pi d is common. So, because of that is taken out, and this is kept inside, this is kept, and this is integral. And if you do integrate, if you integrate this, ultimately you get gamma dc square by 2 plus L minus dc gamma dc and k tan delta pi d. So, this will be outside. So, that means you are getting this one, this expression is giving you the load taken by a pile because of the skin friction only, and that too when the pile is driven in the sand. Okay. So, what you have to remember, gamma dc square by r, or no need to remember, if you calculate this way based on the fundamentals, actually you do this way and this way, and then if you integrate this one ultimate and you keep this thing outside, then you will get, you should say gamma z, actually gamma z dz. So, gamma z dz actually if you integrate, so it will be gamma z square by 2, and then if you put limit, so ultimately gamma dc square by 2, that is what it has come. And here actually there is no variable. So, L minus dc gamma dc is there, k tan delta pi d. So, this is actually unit that skin friction of the pile. Now, we have to find out. So, L is the length, d is the diameter, k is the coefficient of active earth pressure or lateral pressure. Next, we have to find out the base resistance, and you can see for the base resistance q tip will be q times a tip. A tip actually you know that if the diameter of the pile is same as the bottom, then a tip is nothing but pi d square by 4. So, q is important to find out. Q will be actually if it is I have considered pile driven in sand, then cohesion part is not there, otherwise you could have written C N C plus gamma df NQ plus 0.3 gamma d n gamma I could have written. So, since it is a cohesionless soil, then because of this part is 0. So, both the cases actually C and C is not there. So, that means Q ultimate for cohesionless soil is gamma df NQ plus 0.3 gamma d n gamma for circular pile. You have learned in the bearing capacity of soil shallow foundation. Similarly, Q equal to gamma df NQ plus 0.4 gamma b n gamma for square pile. This is also we have learned in shallow foundation or bearing capacity. So, these are principally they are same, and there are lot of theories available for bearing capacity estimation of pile, but we will not go in detail, but what final recommendation is given which will be useful for you, that I will discuss. And here actually I will give you whatever notation used that I have explained. Q is the bearing capacity at the pile tip, gamma is the unit weight of the soil, df is the embedded length of the pile. That means, if this is the pile and this is here, this is actually df. So, embedded length of the pile n q and gamma are the bearing capacity factor, d is the diameter of the circular pile and b is the width of the square pile. Okay. Width of the square pile, or even if it is circular, that means it will be similarly diameter. Now, you can see here some discussion I have made here. It can be noted that the equation have the same general form as the bearing capacity equation of shallow foundation, as I have already mentioned. The magnitude of effective vertical pressure of soil adjacent the pile is more or less constant below the critical depth, is it not? So, that means, if the pile is here and this is I am considering df, then here actually gamma times df nq that we are considering, as I have mentioned that already previously, that adjacent the pile is more or less at critical depth is constant. So, we take pressure diagram something like this, is not. So, instead of gamma df nq, what we can take gamma dc actually, that is what. Thus, for design purpose the term gamma df nq should be replaced by sigma v dash tip nq, where sigma v dash tip is the effective vertical pressure adjacent the pile at the pile tip. And how to do that? As we have restricted horizontal pressure here, same pressure will be here. So, that means, it will be nothing but gamma times dc multiplied by k. So, that is the effective vertical pressure at the pile tip. Further, in most cases driven piles are relatively small in cross section, therefore, the terms involving d and b are small compared to other terms in the equation. So, you can so that means, whatever equation two terms you have got, we have got one gamma df nq and another is 0.4 b gamma n gamma. So, instead of gamma df, we have to take gamma dc, that is one thing. And second thing is the second part 0.3 b gamma n gamma, that part, and the first part gamma df nq, that part if you consider, and you will see that the second part value is quite negligible. So, because of that, what we do, we consider the bearing capacity of the pile, we express by this equation. We consider q equal to sigma v dash tip nq, and this nq is not the same nq of shallow foundation nq. We will discuss that actually in the subsequent lecture. For the time being, I will tell you that sigma v tip means if there is a pile something like that, then gamma df actually, as your equation says gamma df nq, but instead of df we take, since it is restricted. So, it will be gamma dc nq to be taken, and then instead of nq, then we can say nq star, and this gamma dc actually nothing but this one, and nq to be estimated separately for deep foundation. Whatever we have learned nq nc for shallow foundation, that cannot be used here, because of this depth effect the value will be different, it will be more in fact, and that thing I will discuss in the next part. So, for the time being, as I have mentioned that pile capacity will have two component, one is the frictional component, another is base resistance component. Frictional resistance, what is the value? Frictional and base resistance, what is the value? Separately you have calculated. These two if you add, then that becomes the pile capacity. I will take that part in the subsequent lecture. With this I will stop here. Thank you.